Hmm? Yeah. Mhm. I guess I scared everybody away. Where is everybody?
Maybe some people are out trying to vote.
Hmm. I voted by absentee.
Me too.
Much easier.
Very much easier.
I'll give people another minute and then I'll start. Well, last time was pretty tough with all the analysis, right?
Well, if you ask me, it's I can't follow the analysis at all. Just
Yeah.
completely underwater.
Yeah, all these Sobolev spaces and Sobolev norms. It takes a while to get used to it. It's not actually very deep. I mean, if you try to think about what an L2 function really is, you can get very confused. But, you know, once you sort of stop worrying about what they look like and just use their properties and treat them, it, you know, pretty easy.
Yeah, well, I have no facility at all with the formalism. I never really, well, I learned something about L2, but I don't think I ever read the definition of Sobolev space until last week.
Mm-hmm.
Or Frechet space either.
Right. Now, Frechet spaces are tough to work with. You usually, yeah, it's really, really tough to work with Frechet spaces. It's not even the inverse function theorem holds for Frechet manifolds or Frechet spaces. So you're really in trouble. All right, well, I have, if not a quorum, at least a few people. So why don't we start? So today I want to talk about Bott periodicity. And there's a version for the unitary group and for the orthogonal group. I'm only going to talk about the unitary group. Proof for the orthogonal group is very similar, though it gets a little more intricate, but the basic idea and approach are exactly the same. So I'm going to stick to the unitary group. I am recording, right? Yeah. Okay. So just to remind you, the unitary group UN is a subgroup of GLNC invertible n by n matrices that satisfy A conjugate transpose is A inverse. And if you look at the Lie group, if you look at the Lie algebra, the tangent space at the identity, you get the matrices, which would be the derivatives at the origin of these matrices that satisfy A conjugate transpose is minus A. These are so-called skew Hermitian matrices. And it's often easier to work with I times a skew Hermitian matrix, which is then a self-adjoint matrix. It's a Hermitian matrix. And so these are self-adjoint. So we can apply the usual theory of self-adjoint matrices to I times A. Anyway, we of course have the determinant map from UN. We go to C star, but because these are unitary matrices, the determinant goes to S1. And SUN, the special unitary group, dimension n, is simply the kernel of the determinant. So this is the SUN is the matrices in UN, unitary matrices, such that the determinant of A is 1. Okay. And of course, another way to think about unitary matrices, they're just complex matrices whose columns form an orthonormal or orthonormal basis of Cn. Now, there's a stability in the homotopy groups of the unitary groups. And the way to see that is to consider the fibration, or the action actually, of UN on UN plus 1. Well, maybe I'll back up a second. UN is included in UN plus 1 matrices in block form. So if A is a matrix in UN and you extend it to make an n plus 1 by n plus 1 matrix in this way, you get a matrix in UN plus 1. And that's a group homomorphism, embeds UN as a sub-Lie group of UN plus 1. If you take the quotient UN plus 1 modulo UN, there's a diffeomorphism of this to the unit sphere in 2n plus 1 space. So that's a sphere of dimension n plus 1. You simply take an A in U n plus 1 and you send it to A of the last unit vector, the vector 0, 0, 0, 1. And the point is that this subgroup stabilizes that vector. Obviously, if you take a vector like this and multiply it by a matrix in UN, something like this, you get back the same unit vector. So this stabilizes the unit vector, and therefore these right cosets act the same way on the unit vector. That's a map from UN plus 1 mod UN to the sphere in Cn plus 1, and it's clearly a diffeomorphism. Okay, it is the space of left and right cosets of UN inside UN plus 1. So in particular, you have a fibration, a locally trivial fibration. And from the homotopy long exact sequence, you see that you have pi I of S2n plus 1 goes to pi I minus 1 of UN, goes to pi I minus 1 of UN plus 1, and so on. Since these homotopy groups vanish when I is less than 2n plus 1, you see that pi I of UN to pi I of UN plus 1 is an isomorphism for I less than 2n, and it's surjective for I equals 2n. So these homotopy groups stabilize. You can take the limit of the unitary groups under these inclusions. and you get something called the infinite unitary group, usually just denoted U. This is a set of infinite by infinite matrices which look like some finite unitary matrix and then the identity. So this would be an infinite identity, and this is a finite n by n unitary matrix for some n, okay, under the natural inclusions. So that's the unitary group, and this stabilization implies that pi I of u n is isomorphic to the homotopy groups of the stable unitary group for I less than 2n and surjective for I equals 2n. Okay. In fact, if you go back to this fibration, you can now iterate and you see a tower of fibration. So un plus 1 is made of a tower of fibrations where the bases are the odd spheres from 1 up to 2n plus 1. Mm-hmm. Okay. All right. Now let me talk about the classifying spaces for the unitary groups. So consider the Grasmanian, this is over C, of n planes in n plus k space. Mm-hmm. So these are, we have Cn plus k, and I just have a linear subspace, an n-dimensional linear subspace, complex linear subspace L. So this makes a smooth manifold, a complex manifold. Its complex dimension is n times k. And in fact, the tangent space to the Grasmanian at a plane, an n-plane P, is just the homomorphisms from P to P perp. You can vary to first order, you can vary this plane by moving it in the perpendicular direction. In fact, these spaces are related to the unitary group, the Grasmanian of n planes in n plus k space is simply the unitary group of dimension of index n plus k divided by the product of the unitary group of dimension k and n. This subgroup is a subgroup of matrices of this form, A and B being unitary of degree n and k, and then zeros here. So any matrix like this fixes the first n plane. And in fact, this is the full subgroup of the large unitary group that fixes the plane spanned by the first n tangent vectors. So you send an element in U n plus k, A in here, to A acting on the plane spanned by E1 up to En. That's an n-dimensional plane in Cn plus k, and that gives you a diffeomorphism between the coset space here and the Grasmanian. Now, an easy exercise from, well, let me not do that. Now we can form the infinite Grasmanian of n planes in infinite space, just let k go to infinity, and this is U infinity, just U modulo U n cross U. So this is the subgroup of infinite unitary matrices which have a block n by n here, 0, 0, and then an arbitrary element of u down there, which is again got to be finite. And then we have the homotopy groups pi I of u n cross u from the, sorry, back up. From the, so we have a fibration, locally trivial fibration, un cross u into this Grasmanian. Get the homotopy long exact sequence, pi I of un cross u into pi I of u into pi I of the Grasmanian, and so on. But this map, well, this group is simply pi I of un, direct sum pi I of u, and it's not too hard to see that this map sends the second factor isomorphically to pi I here. So you get from this long exact sequence that pi I of the Grasmanian is isomorphic to pi I minus 1 of the unitary group. In fact, the Grasmanian is the classifying space for the unitary group. There is, over the Grasmanian, the frame bundle. So frames, in frames in infinite space. This is simply the space of n orthogonal unit vectors, an orthonormal subset of rank n inside infinite dimensional complex space. This is the map that takes a frame and associates to it the plane that the frame spans. The unitary group acts, un acts, on the frames by just acting on the frame, and the quotient is the Grasmanian. But this space is contractible. And the idea is that if you have an infinite frame, an infinite frame, an n frame in infinite space, you can simply get a unit vector by taking the last element of the frame, and that's a fibration, and the fiber is n minus 1 frames over infinity minus 1 space, but that's still infinity. And by induction, you argue that this is a contractible space. This is a contractible space being a sphere in infinite dimensions, so the frame bundle is contractible. And then from the homotopy long exact sequence, you again get pi I of the Grasmanian is pi I minus 1 of the unitary group. And indeed, a similar argument shows you, in fact, that the loop space of this Grasmanian is homotopy equivalent to the unitary group. So this is the classifying space. It's the classifying space for the unitary group. It's often written BUN. BUN is a space well defined up to homotopy related to the unitary group. Has a principal UN bundle over it with contractible total space. Okay, and any time you take the classifying space of a group, you get a homotopy equivalence between the loop space of the classifying space and the original group, and then you get that the homotopy groups are shifted by 1. Okay, so that's general theory. It applies for the unitary group. It applies for any compact Lie group, in fact, any Lie group. Bott periodicity says the loop space on the special unitary group of, let's say, dimension 2n, well, back up here. I'll state a finite theorem and then I'll state the infinite theorem. There exists an embedding of the Grasmanian, complex Grasmanian of n planes in 2n space into the loop space on SU 2n, inducing an isomorphism on homotopy groups for I less than 2n. Got what I mean? Yeah. Okay. So this is Bott. This is a sort of finite form of Bott periodicity. And the sort of more standard form of it, the theorem pi I of BU is isomorphic to pi I plus 1 of U. So the point is that because of all the stabilities, for I less than 2n, pi I of this Grasmanian is identified with pi I of BU, and pi I of the special unitary group is, sorry, this should be a special unitary group. Yeah. So as you if you replace the finite objects by the infinite ones, this map is an isomorphism on homotopy groups up to dimension 2n. This is an isomorphism on homotopy groups up to dimension 2n. These inclusions give you then isomorphisms of these homotopy groups. So this is the usual form of Bott periodicity, because it implies that pi I plus 2 of SU is pi I minus 1 of U. And of course, pi I of SU is equal pi I of U for I greater than 1, since we have the fibration. And the circle has a non-trivial homotopy group only in degree 1. And this SU is simply connected, and therefore this maps an isomorphism on pi 1, and all the other homotopy groups of U are the same as SU. So putting these two together, you see that pi I of U, pi I plus 1 of U, is isomorphic to pi I minus 1 of U for I greater than or equal to 0. And then we get the sort of classical periodicity statement, pi I of U is isomorphic to Z when I is odd and 0 when I is even. This comes from the fact that pi 2 of SU is 0 and pi 3 of SU is Z. And you go by, and then you also use the isomorphisms that pi 2 of U equals 0, and then pi 3 of u equals z. And then you just induct. Once I know, well, pi 1 of u equals z. Once I know pi 1 of u is z and pi 2 of u is 0, then this says the groups are periodic once you get, well, yeah, sorry, this should say I greater than or equal to 1. So pi naught of u is pi 2 of u, pi 1 of u is pi 3 of u, pi 3 of u is pi 5 of u, pi 5 of u is pi 7 of u, and so on. So there's a 2 periodicity in the unitary groups. Just by way of comparison, for the orthogonal group, the periodicity, it's a little more complicated, is raises index or lowers index degree by 8, whereas in the periodicity in the unitary group it's only 2. And there are lots of other interesting classical spaces, homogeneous spaces related to the orthogonal group that come into this periodicity. In particular, when you go by 4, you get the symplectic group. So it's a more complicated theorem, but it's a similar nature. So this has nice consequences for K-theory. For example, we can now compute the K-theory of isomorphism with a growth and group of vector bundles over the sphere. Well, there's always the degree. So this is n odd. You have the degree, which gives an isomorphism, vector bundles over the sphere, and the growth and group to the integers just given by the degree of the vector bundle. And for even spheres, you get the degree and the Chern class divided by the sort of minimal Chern class you can get. Okay. And that comes out of the fact that, say, the kernel of the reduced K-theory is simply maps of the sphere into BU, which is pi n of BU, and we know that to be 0 or Z in odd, in even, and this is the reduced K-theory, the kernel of the degree map on the sphere. Okay. And there are lots of other results. The reduced K-theory of the two-sphere wedge of space X is the same as the reduced K-theory of X. So you get a periodicity. This is very closely related to the K-theory of S2 cross X. There's some trivial factors you have to take out. So the K-theory of S2 cross X is completely determined in terms of the K-theory of X and other trivial factors. Okay. So these are forms of Bott periodicity and their applications to vector bundles. All right. Let me give you a sense of how the argument is going to go by doing a related but much simpler case. I want to calculate a stability result for the homotopy groups of spheres, which is well known by other computations, but I want to give you sort of indicate how a Morse theory approach would take that, would do that. So I'm going to consider the sphere with its round metric, Sn. I have the south pole and the north pole. And I'm going to consider the loop space. That'll be this L12 paths, but let's not worry about that. Let's make this Sn plus 1. So geodesics in, well, paths in Sn plus 1 that start at the south pole and end at the north pole. Okay. So what are the critical points? Well, critical points, of course, we already know, are geodesics. And we know what geodesics on the sphere look like. They look like great circular arcs. Right? And of course, the arc, well, it's an arc for a while. It starts at the South Pole. After some finite time, it will reach the North Pole. It will continue back the backside, back to the South Pole, and it'll just wrap around and around and around. That's what geodesics look like. Yeah. So let's think about the space of minimal geodesics. Okay, from S to N. It's pretty clear what those are. These are half great circles. Because any other geodesic, so the half great circle will have half the circumference of any great circle. So half the circumference. The next smallest, shortest length geodesic would be to continue that back to the South Pole and come back to the North Pole. So it would be 3 times as long, and then 5 times as long, and 7, and so on. So the minimal geodesics are great half circles. They're not isolated. The manifold of these is the equator Sn inside Sn plus 1. Because if you have any half great circle, it's completely determined by the point in the equator where it crosses the equator, and then it does that only once. So the space of minimal geodesics is Sn inside the loop space. I claim all other geodesics, that is all non-minimal geodesics, have index greater than or equal to 2 times n minus 1, 2 times n. Okay. I'll say a word about that in just a second, but then we see that implies that the inclusion of S, that implies that the loop space of Sn plus 1, South Pole, North Pole, is homotopy equivalent to the space of minimal geodesics union cells of dimension greater than or equal to n. Okay. So that tells us that the homotopy groups, the inclusion of these minimal geodesics into the loop space gives an isomorphism on homotopy for I less than 2n minus 2, I guess. Well, less than or equal to n minus 2. But this, of course, pi 1 of this path space, the path space is homotopy equivalent to the loop space, the actual loop space. So this is the same as pi I of the loop space of the sphere, Sn plus 1, based at some, let's say, North Pole. Maybe I should call it the South Pole. Too many n's. And that's pi I plus 1 of Sn plus 1. So we have an isomorphism called the Freudenthal suspension theorem. Pi n plus 1 of Sn is isomorphic to pi n of Sn for I less than or equal n 2n minus 2. Okay. Now, why are the other non-minimal geodesics of index at least 2n? So there's a theorem, I'll state it in more detail in just a minute, that says the index of a geodesic, gamma mapping 0, 1 into a manifold, this is a general result, is equal to the sum of all spaces, sum of the dimension of all spaces of Jacobi fields vanishing at 0 and t in 0, 1 open. So you sum over t. It turns out there are only finitely many t between 0 and 1 for which there's non-trivial Jacobi fields vanishing at 0 and at t. You have finitely many t for each of those t. You take the dimension of those Jacobi fields vanishing at the two endpoints. And you add those up, and that sum is the index. So in our case, just see how this works. For the minimal geodesics, the Jacobi fields don't vanish before this point n for this minimal geodesic because the differential of the exponential map is a diffeomorphism. The first time there are Jacobi fields is when you hit the North Pole, and the dimension of those space of Jacobi fields, well, the exponential map from the South Pole takes the sphere of whatever this radius is, I guess pi, a sphere of radius pi, and collapses a sphere of radius pi onto the North Pole. And therefore, the kernel of the exponential map at any one of these geodesics is the tangent to that sphere and has dimension n minus 1. So the dimension of Jacobi fields that vanish at S and N is n minus 1. I'm sorry, n. This is Sn inside Sn plus 1. So there's an n-dimensional space of Jacobi fields vanishing at n along this minimal geodesic. If you keep coming back around, there's no points where the Jacobi fields vanish except when you get back to S, and then you have the full sphere of radius 2 pi, and the exponential map sends that sphere onto the South Pole, and therefore, once again, you see the kernel of the exponential map here has dimension n. So every time you pass either the North Pole or the South Pole, this geodesic crosses one of those points, you add an n-dimensional space you have another n-dimensional space of vanishing Jacobi fields. And therefore, if you take the next minimal geodesic, you start here, you cross n, you get an n-dimensional space, you cross S, you get a second n-dimensional space, you come back to n, you don't count the ones vanishing at n, it's only the ones that vanish before the endpoint. So those geodesics give you a 2n dimensional space for geodesics of length 3 pi, and then so on. Then you'd have a 4n dimensional space for geodesics of length 5 pi, and so forth. So all the handles that you're adding, well, all the other critical points have index at least 2n. And that index is computed using Jacobi fields that vanish at intermediate points along the trajectories. And for these spheres, we only add when we cross, we only add new Jacobi fields vanishing along the curve. When we pass, we cross either n or s. And we always add an n-dimensional space when we add one. So that's why the other the indices of the non-minimal geodesics are at least 2n. Well, the argument for the unitary group is going to go very similarly. So, well, for SU 2n, we do a very similar argument. The minimal geodesics turn out to be, are the Grasmanian of n planes in 2n space. So what replaces the equator in this argument is a Grasmanian. These are Bott Morse, Bott Morse. And all other critical points have index greater than or equal to, I guess it's 2n. Okay, so that implies, sorry, I'm going to do SUN and I'm going to do the loop space, put it here. I didn't say which loop space. I'm going to do the loop space in SU2n from the identity element to minus the identity element. So the matrix with -1s down the diagonal is an element in SU2n because I have an even number of -1s. And the minimal geodesics in this loop space turn out to be the Grasmanians of n planes in 2n space. That's a Bott Morse critical set. All the other critical points have index at least 2n, and therefore you see pi I of the inclusion of the Grasmanian in the loop space gives you an isomorphism on the homotopy groups. For I less than or equal to n minus 2. Okay. So that's the original, that's the core of the Bott argument. And then you soup up using stability and so on to get the usual forms of periodicity. All right. Once again, the computations of the index are made using this theorem that says the index is related to these families of Jacobi fields that vanish at various points along the curve. So those computations have to be made in the unitary group. Okay, and I will show you in more detail as we go along how these computations work. I just wanted to indicate, try to draw the analogy that you have an understanding of where we're headed. The analogy with the sphere, which is much easier to understand. Okay, so let's talk about geodesics in the unitary group. So first I have to give you a Riemannian metric. So on the tangent space to the identity, the Lie algebra, we use minus trace AB as the inner product of skew Hermitian matrices A and B. The minus sign is because these are purely imaginary. So a typical element, well, it's a very special element, but it's the kind of element to think about in the Lie algebra would be a purely imaginary diagonal matrix. So entries only down the diagonal, purely imaginary, so the AI are real numbers. And that is clearly a skew Hermitian matrix. And the inner product of this matrix with itself, you see, is simply summation AI squared. So the trace, well, here A is equal to B, so you're just taking A squared, you get minus AI squared down the diagonal. So the trace minus the trace is a sum of the AI squared. So that certainly justifies the minus sign in front of the trace AB. Makes a positive definite inner product on the unitary group. It's invariant under the adjoint action. So this gives you a Riemannian metric. You just push it around by left or right translation, you get a Riemannian metric on the unitary group. Okay. Let's try to calculate. Okay. So the first little lemma is that any alpha in UN is conjugate by the orthogonal group to a diagonal matrix. So alpha is conjugate under the unitary group to a matrix of the type I was just talking about, AI real. And the point is that alpha skew Hermitian, so I alpha is self-adjoint Hermitian, self-adjoint matrix. So there exists an standard argument that we teach our calculus students as an orthonormal basis in which I alpha is diagonal. So in this basis, I alpha is some A1 to AN, AI real. Eigenvalues are real and the matrix can be diagonalized. And therefore alpha is, I guess I've switched the signs here, but they're still real. Okay. So that's how you prove the diagonalization result. So let's think about then the geodesic. So let gamma be the geodesic with, starting at the origin, with gamma dot at the origin is this matrix IA1, IAN, 0, 0. Well, you just have to exponentiate this vector. So gamma of t, not too hard to see, is e to the I A1t, e to the I ANT. That's certainly a family of matrices. It's not hard to prove it's a geodesic with respect to this inner product. It's the tangent vector self-parallel, and it has tangent vector at the origin, clearly given the given vector. Okay. So any geodesic through 0 or 0 0 is conjugate under the unitary group to such. So these are up to conjugation by the unitary group. These are all the geodesics that go through the origin. Okay. So now I want to go from 1 to -1. So I want gamma of 0 to be the identity element and gamma of 1 to be minus the identity element. -1's down the diagonal. Well, that implies, I mean, these conditions are invariant under conjugation because the identity and minus the identity are central elements, so they're fixed by conjugation. So I might as well suppose my geodesic is of this diagonal form. And what that implies is that the AI have to be odd multiples, odd integral multiples of pi, because I need e to the I AJ pi, AJT to be minus the identity when t equals 1. So I need e to the I aj is minus the identity, is minus 1. Sorry, this should say minus 1. So minus 1. So that's just saying each one of these exponentials has to evaluate minus 1 at t equal 1. That is to say, you have to have this formula, which implies aj is an odd integral multiple of pi. Okay. Now suppose that we work in, now let's work in SU2n. So our matrices are even size, but we have the determinant is equal to 1. That's, in terms of the AI, simply says the summation from I equals 1 to 2n of AI equals 0. And I'm going to switch notation because these things are all integral multiples of pi and replace AI. My diagonal entries are now going to be AI times pi. Okay. So here's what I'm looking at. I'm looking at something conjugate to e to the I pi a1 of t, e to the I pi a2n of t, where the summation from I equals 1 to 2n of the AI is 0. That's my geodesic. What's the length of this geodesic? Well, it's the square root of the integral from 0 to 1 of the length gamma dot of t squared dt. Well, gamma dot of t, gamma dot of t is simply the trace squared of the diagonal matrix we computed before. It was, now that I've switched notation to pi I will get pi ai squared sum. That's constant. The length of geodesic, length of the tangent vector of geodesic is constant. So I'm integrating this from 0 to 1. That's just multiplying it by 1. I equals 1 to 2n. So pi squared. So we get pi times the square root of the sum of the ai squared. I equals 1 to 2n. And this is all subject to the condition that the ai add up to 0. Okay. So let's think about what the minimal geodesics are. So I have to minimize the sum of the squares subject to the condition that the values add up to 0. Well, it's pretty clear the only way you can, the minimization of that is to take n of the ai equal plus 1 and n of the ai equal minus 1. Then the sum is clearly 0, that's fine. And the summation from I equals 1 to 2n ai squared is 2n. So minimal geodesics have length pi square root of 2n. and are determined by an n-plane, a complex n-plane in C2n, namely, let's say, the plus I pi eigenspace of gamma dot of 0. Okay. So recall, after you conjugate, gamma dot of 0 looked like I pi a1, I pi an. You need the ai to be odd integers. You need their sum, the 2n, you need their sum to be 0, and you want to minimize the sum of the squares of the ai's. So the way we did it was to take half of them plus 1 and the other half minus 1. So I see two subspaces inside Cn. The n-dimensional subspace spanned by the vectors where ai is positive, and the n-dimensional space spanned where ai is negative, and those are perpendicular. So the invariant is the plus I pi eigenspace, which is one of the coordinate coordinate hyperspaces for this diagonal matrix. But in general, I can conjugate gamma by any unitary transformation, and therefore I can move the plus eigenspace into any n-dimensional subspace. The minus eigenspace will simply be the orthogonal. So the space of minimal geodesics is the Grasmanian of n-planes in 2n space. Okay, so this is what plays the role of the equator in Sn plus 1. Okay. So those are our minimal geodesics. So I have to prove lemma this subspace is a Bott Morse critical submanifold, meaning I have to prove that the kernel of the Hessian at every one of these geodesics is the tangent space to this Grasmanian. It's no bigger. And then I have to show theorem, the index of a non-minimal geodesic is greater than or equal to 2n. I think it is. Okay. So that's how we go about proving Bott periodicity. We've got this critical submanifold, which gives us a copy of the Grasmanian inside the loop space. We want to compare the topology of the two. So we want to see that the loop space of S2n loops beginning at the identity and going to minus the identity is written as the Grasmanian in homotopy theory, the Grasmanian of n-planes in n-space union cells of dimension greater than or equal to 2n. And then the homotopy theory tells you the Grasmanian and the loop space have the same homotopy groups up to 2n minus 2. Okay. So that's how we're going to do it. I think what I want to talk about next is, so in order to compute the index, we need, as I indicated before, a computation in the unitary group, in the special unitary group, of what the Jacobi equation looks like, explicit computation. And then I need this general result that compares the index to this sum over the previous times of the dimension of space of Jacobi fields that vanish at the origin in that time. That's a completely general result. So I want to start with the way you do the computation of what the Jacobi equation looks like and what the Jacobi fields look like in SUN. And much of it can be done in a much more general context, namely in the context of a symmetric space. And as probably most of you know, and it's not hard to see, and I'll show you, any Lie group is a symmetric space. So I'm going to stop with the special case of the unitary group and just study for a while the loop space, and in particular the Jacobi equation in a symmetric space. Becomes a much easier discussion in a symmetric space. So I guess I should remind you what a symmetric space is. X is a Riemannian manifold. And for each point X in X, there exists an isometry fixing X, whose differential at X is minus the identity. So that symmetry is, this manifold is somehow around every point, it's symmetric in the sense that you can reverse the direction. There's an isometry fixing the point and reversing all directions. So if you have, for example, and that has to be true for all X. So this has to be true for all X in X. There has to be a symmetry like that at every point. So if you have a geodesic through X, gamma, and you apply Tx of gamma, you get a new geodesic, which in fact is the same as gamma, except the direction is reversed. So gamma was, say, moving in this direction, and T of gamma, Tx of gamma is a geodesic moving in the opposite direction. So geodesics are fixed, geodesics through X are fixed by this symmetry Tx, because it's an isometry and it's -1 on the identity. So you can do nice things like this. Suppose you have a geodesic and its value at P is, its value of 0 is P and its value at A is Q. Right. Suppose you take, so this is gamma, suppose you take TP of gamma. So you invert gamma at P, you get the same geodesic, but now you move back here to -A, because this thing is flipped over. And now take symmetry about Q of that. So now you flip about this point and you go up to, well, maybe I shouldn't have done that. Sorry. Making my life too complicated. Suppose I just do, sorry. Suppose I just do TQ of gamma. Do I have gamma from 0 to A? Let's start over again. So I have a geodesic from P to Q defined on time 0 to A, say by unit speed. And now I flip the geodesic at Q. So here's gamma, here's TQ of gamma. So now this is a geodesic arc and this is a geodesic arc, and they have the same tangent vector at Q. So in fact, they fit together to make a geodesic. So gamma union TQ of gamma is a geodesic from 0 to 2a, defined on 0 to 2a. So that implies symmetric spaces are complete. If you have a geodesic, you can always extend it by well, an arbitrary amount. You just keep doing this to make it as long as you want. So geodesics extend forever. So symmetric spaces are complete. And now if you do TP compose TQ of gamma of T, you get gamma of T plus 2a. So if you have a geodesic gamma and you flip around P and then you flip around Q, that corresponds to translating along the geodesic by twice the distance from P to Q. So this is just a translation along the geodesic. Gamma by 2a, assuming these are parameterized by arc length. Okay? So that's my brief introduction to symmetric spaces. And that here is the main lemma that we use for symmetric spaces. It makes the computation of Jacobi fields so much easier. So we have the Riemannian curvature tensor R. And remember, if you take any pair of tangent vectors in general at a point, this is an endomorphism from the tangent space at the point back to itself. Okay. So I'm going to be considering the curvature quantity that comes up in the Jacobi equation. I'm going to suppose I have a geodesic gamma, and I'm going to consider RW gamma dot along gamma. So gamma dot's a tangent field along gamma. W is supposed to be a tangent field along gamma. Okay. Okay. And my claim is that this, if W is parallel along gamma, that is, the covariant derivative of W is 0 in the gamma dot direction, then RW gamma dot is parallel along gamma. So this is in a symmetric space. I'm assuming here I'm in a symmetric space. Okay. Well, what I need to do is take another vector field X parallel along gamma and consider R gamma dot inner product with X. If this is parallel for all X, that implies RW gamma dot is parallel. Sorry, if this is constant, I shouldn't say parallel. If this inner product is constant along gamma for all X, that's what it means for this thing to be a parallel field. You would just take the covariant derivative of take the d by dt of this expression. It's a sum of the covariant derivative on this one applied to X plus this one applied to the covariant derivative of x. Covariant derivative, well, I'll do it. D by dt of the inner product is the covariant derivative x plus covariant derivative, which is gamma dot, of course. This term vanishes because x is parallel. This term vanishes because I'm assuming that this inner product is constant. So if the inner product is constant for every parallel x, we see that the covariant derivative against any parallel x is 0, and that implies the covariant derivative is 0. Implies that this thing is parallel. Okay, so that's what we have to prove. We have to consider RW gamma dot x, where W and X are parallel along gamma. What am I doing on the time? Okay. Well, so what is the curvature operator? It's covariant W, covariant gamma dot on gamma dot, minus covariant gamma dot, covariant W on gamma dot, minus the covariant derivative in the commutator of W gamma dot on gamma dot, all that inner product X. Okay, now there's a little lemma in I'm doing this wrong, yes. So I use these symmetries T that I have. So T is an isometry, just translation by 2a along gamma. Okay, this was a product of flipping at P and flipping at Q, when P and Q are separated by A. You get a translation by 2a along gamma. But T is an isometry, so R of TW T gamma dot T gamma dot Tx is equal R of W gamma dot X, because T is an isometry. On the other hand, because TP of WP equals minus WP, since TP is a, remember T here is TQ TP. So TP fixes P and is minus the identity on the tangent space. So that's where this equation comes from. But now W is parallel. So that implies TP of W is minus W everywhere. And likewise for TQ of then TP of W is minus of W, which is W. I'm sorry, I'm getting myself so confused. I want to compare this expression, which is the covariant derivative shifted at a point shifted by 2a with the inner product at the original point. But what I do is I use the fact that T fixes all these parallel vector fields, and therefore, I'm sorry, I'm going to start here next time. So I'll start here with the computation of what this expression, which is the one that comes into the Jacobi equation, looks like in a symmetric space next time. I'm sorry, I just got lost in this argument. So I'll start with this lemma again. We will make the computation in a local symmetric space. Generally, we will then make the computation in the special unitary group, and we'll be able to evaluate both the Hessian at minimal geodesics and the index of non-minimal geodesics by an argument that's reminiscent of what happens in the case of the sphere. So that's what I'll do next time. And I apologize for getting so screwed up in this last argument. Any questions? Well, if there are no questions, I'll take this up again on Wednesday. Thanks. So long.